Okay, just a reminder to you that the final exam is mandatory. You must attend unless you're a special study group leader, and I give you permission to skip the exam. Uh, in addition, you have to be in the right location, and you have to be there on the right day at 1 o'clock Saturday, December 10th. And we're going to be down the hall in room 201. Now, I'll be going back and forth between this room and 201, but you guys have to be there. Now, the reason you have to be there is because when we grade it, if you were in this room, this room goes to a separate grading process, and then it's going to look like yours won't be graded because it's expecting Section 1 grades. If you're in the pile from this room, you're not going to get a grade. So you got to be in the other room, and then you'll get a grade, and then you won't have a big disaster. Okay. Now I'm going to bore you to tears, hopefully, with this little nugget of information, because I want everybody in the room, especially guys in the back row, to make sure that they're here. And I don't want anybody on exam day or the day after saying, Dr. B, I thought the exam was, this other day, and nobody was there, so I thought you canceled it. No, this is the day. Saturday, December 10th. You must be there. All right, let's get down to business. We're going to talk about resonance and standing waves and stuff, and oscillating systems in general today. But before we do that, and we're going to have homework 12, that'll be running at 1:20 p.m., I think. Okay, it's ready to go and a bunch of questions. But before we do that, a few things for the good of the order. Specifically, there's a new line in your grades page, actually 3 new lines. The important one is the one that says participation pointage estimate as of October 13th. Now that's as of exam 2. And it looks like this on the bottom of the grades page. Here it is down here. And just a side note, do not pay attention to any of the numbers that purport to be grades from me. There are no grades from me. There are only data in the grade book right now. There's no grades. This gray rectangle at the very bottom, don't pay any attention to that, and you'll be save yourself an enormous amount of confusion. Now, this line down here is based on how many questions you've answered up to October 3rd, actually up to October 11th. Now, last week is not on the books yet, all right? And so it's been a little bit tricky with iClicker. As you know, I've had some iClicker fails up here in the front this semester, and we're still not to the bottom of it. But anyways, this line in your grades page is your participation pointage if I were to do your semester grades today. So it'd be out of 25 possible. And now that you have this grade, this number, you can estimate your own semester grade as of October 13th. So up to exam 2. Now, I'm going to be doing more grades we're going to be doing more clicking this week, and we're going to be doing more exams and stuff, but you can, we're going to be doing more homework and stuff. So things will be changing, but not by a whole lot. And you can put together your grade, estimate your grade, the way that I showed you how to do on Thursday last week. Okay? Questions about that? Okay, let's keep going. I want to talk about the estimates of your semester grades that I did. And basically, right now in this class, there are 505 students who have taken both exams. Now, That means there's a few dozen that have missed either exam 1 or exam 2 or both. Now, students that have missed one exam, you've got to be here for exam 3, and then you'll be able to figure out your semester grade estimate. But for 505 of you, you got 2 exams on the book, you got clicking on the book, and you got homework on the book. So what I did was I figured out letter grades for everybody. The class average right now, in terms of 150 points possible, 50 points for exam 1, 50 more points for exam 2, 25 points for homework, 25 points for clicking, participation, total of 150, and without adding in any bonus points, the class average is 77%. Now that would be a B. It's a little bit high. I usually like to have the grade about 75%, around in there. But it's all right. 77 is good. I like it in the 70s somewhere. You guys are really smart. And so I want to show you how the letter grades stack up. In other words, I gave everybody an estimated grade as if I were doing semester grades. I did it all yesterday morning. And this is the way the distribution of letter grades is. All right? Now, I want you to take a look at that. I'm going to ask you some questions. I want you to visually eyeball this. Okay? All right, now this is according to my grade scheme. 90% performance for an A. 75% performance for a B. 60% performance or higher for a C. 50% performance or higher for a D. And below 50% an F. Now if you look at that, you'll see there are, of the people that took both exams, there's not many Fs or Ds. Nice. But by the same token, there's not a whole big pile of A's either. It's a good pile, but it's not a huge pile. The big pile is the B's. Right? That's good. The average is 77%. That's a B. So the biggest pile should be, the B's. So this is the grades that, that if I were to end the semester today, this is what they would look like. Now, on the syllabus, you may remember that it says that I do not grade on the curve. And I'm going to show you why. This is the grade distribution using the curve. I want you to look at that carefully. Now, this is a curve in the standardized method, for instance, like they use on the SAT. SAT is based on 500 SAT being at the average score, the average performance. And everybody above that and everybody below that, they give numbers and stuff to your SAT, and the GRE is similar. Right? So this is based on the curve. Now take a look at that and compare it to this. Here's the Dr. B grade distribution. All right, look at it carefully. Now look at the curve. You guys that have grade printouts for I have grade printouts for you guys that you asked me to do last week. I have them this week. Dr. B, distribution of grades. You see anything? What do you see that's different? The curve. The true distribution of grades. Here they are together. I want you to look at that. Raise your hand if you see something. What do you see? There's more C's and less B on the curve, you mean? Looks like the C's are about the same, but B's are definitely less. All right. B's definitely less. There's more D's. The D's are more. There's more A's. Yeah. Now, let's look at this first observation. Fewer B's. A bunch of those B's that I would give, the curve says, no, 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 you're a C. And they get slapped down here into the C's. So the effect of the curve, one of the effects anyways, is that the curve empties out the B's. That's no good. And here's how many students it happened to. 53. That's 19% of all the students that I wanted to give a B to. The curve says, no, 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 you have to have a C. That's no good. Now, let's take a look at this. Somebody said there's more D's. Yeah, and you know where they came from? They came from the C's. There's a bunch of students that I wanted to give C's to, but no, the curve drops them into the D's. How many? 56%, or 56 students, 39%. 39% of all the students that I wanted to give a C, the curve says, no, no, no. Those have to be D's. That's no good. Now, somebody said, Dr. B, there's more D's in there. There's more F's in there too. Look at that. You see that? The D, it goes all the way down the D's. You're thinking, oh, I'm just scraping by with a D. No, not on the curve, man. The curve cuts a bunch of those D's. And look at this. It's a small pile, but almost 2/3 of the pile gets shifted down to the F's. That's no good. And now, as they used to say on the radio, you know the rest of the story. This is why, Morgan, I do not grade on the curve. I never grade on the curve. I think I did it once just to prove to the students that it sucks badly, majorly. I never do it because I want you guys to break the curve. I don't want you to be victims of the curve. My job is to draw out of you the performance that breaks the curve. And if you earn an A, you get an A. If you earn a B, the curve ain't taking it away from you. I'm going to make sure you get it. You want it, you got it, Toyota. If you earn a C, I'm not going to let some Nimrod curve method take away your C and give you a D. If I was a jerkwad from another planet, maybe I would want to do that. But I want you guys to get great grades. If you all get an A, I'll give everybody an A. I'd love to see that. So you're never going to see this. No. So write down the word curve and then cross it out. And this is what we're going to be using. All right. So the Dr. B method of grading it's tough. I mean, this is tough to flunk, tough to ace. You know, it's tough to get an A, but if you get an A, you got something good. But yet, it's also tough to flunk. Look, there's not a whole lot of people flunking. And those are people that don't do homework and stuff, by and large. Don't come to class. All right, questions about this? Questiones. All right, let's keep going. I'm talking about waves. Waves and oscillatory systems. All right. We took a look at the wave effects, the demonstrations. Let's get to the concepts. Here's concept number one. It's pretty important. Waves are different from Newtonian particles. You know, something that obeys F equals ma. Waves transport energy and momentum across space-time, but they do it in a way that matter is not accelerating or speeding from point A to point B. The waves in the ocean that we get here in Coco might be from a storm off the coast of West Africa. And those waves just roll all the way across the Atlantic. And then they crash into the beach here, and you get in and you surf. But it's not because that storm off the coast of West Africa has pushed all those H2O molecules over here. They're still pretty close to the coast of West Africa. They'll be there for a long time. Ocean currents will move them around, but the waves don't. The waves will move them a little bit. But what moves is energy and momentum. Waves are not usually easy to localize. In other words, you can't put a box around a wave. You can't put a big box around it unless it's the size of the universe, and then you got every wave inside of that. But you can't put a dot on a map or put your pencil. Yep, that's where it is, because it's extended and it's in motion. They behave way differently than a Newtonian particle. The diffraction effects that we saw on the first day of lecture, when we saw the beautiful red H alpha line from the diffraction of the hydrogen light. The resonance effects that you just saw, yeah, that's stuff that particles never do. You can't even come close to achieving that with particles. Another thing that waves do is when they hit the barrier, the edge of a barrier or a gap in a barrier, they'll generate wavelets. And in this picture here, this is a famous picture, this black and white image. It's from like the 1950s, maybe the 1960s. This is an old picture when I was in school, but it's a good one. And it shows water waves going upward into a barrier in which there's a gap. The gap is right here in the middle. I'm putting my cursor over it. The word wavelets is pointing toward that gap. The waves coming into the barrier are like waves in the ocean. They just kind of come in rows. But once that wave interacts with the gap, it's as if somebody's dropping little stones, little teeny pebbles into the water. And here on the other side, you get kind of rounded waves propagating outward. And the theory is that the wavelet theory is that at that interaction site, the wave generates a row of tiny spherical waves, and they all add together to form that pattern that you see above the barrier. That's a diffraction pattern. That is a picture of water waves doing what you guys saw when we looked at hydrogen, helium, and neon on the first day of lecture. So wavelets. That's something that particles will never do. Particles behave like billiard balls. Atoms behave like billiard balls in many situations, but in other situations they behave like waves. It's kind of cool. Now, the simplest wave equation is V equals lambda F. Let's take a look at it. Okay, V equals lambda F. Lambda is the symbol for the wavelength. That's the spatial distance between two corresponding points on the wave. So from peak to peak, from one peak to the next peak, or if you think at the bottom of the wave where it's down deep in the ocean, trough to trough, that's the same distance. That's one wavelength. And then F. F comes from the temporal measurement. Capital T is the customary symbol for the period. And it means the amount of time it takes for one wave to pass you, and then the next wave, from one crest passing you, start your stopwatch, and the next wave passing you, stop your stopwatch. Okay, that's the period. Or let 10 of them pass, stop your stopwatch, and then divide by 10, and that'll be the period. Right? Now, the frequency is the reciprocal of that, 1 over the period. There's a special unit for frequency. You can think of the frequency as being cycles per second. The fancy unit in the metric system for that is Hertz, symbolized capital Hz. It's named after a German scientist named, I think his name was Heinrich Hertz. And he was the first guy in the lab to measure what had been predicted, that electromagnetic waves, if you have the right device, you should be able to pick up electromagnetic waves. And he was, from which we get wireless and radio and everything else. He was the guy that first figured out how to do that in the lab, and now it's a common everyday thing. You don't even think about it. But in his day, in the 1880s, it was pretty new. So the unit of frequency is named after him, cycles per second, or 1 per second, meaning 1 cycle per second. Another form that you sometimes see, S to the minus 1 power. That means, minus 1 means 1 over, so that's 1 over S, seconds to the minus 1. You sometimes see that. Here's another way to describe it. V is the speed of propagation. So that'll be measured in meters per second maybe, or sometimes you'll hear people talk about the speed of sound in miles per hour. And other ways to describe speed. And then the wavelength, that's going to be meters or centimeters. Nanometers, little n, little m. Nanometers, nm. That means a billionth of a meter. Frequency measured in cycles per second, or hertz, capital Hz. Oh, and by the way, Professor Hertz, his last name is spelled like the rental car company. Hertz Rent-A-Car, H-E-R-T-Z. But we symbolize it Hz. Kilohertz, KHZ. And by the way, the AM radio band is from 540 kilohertz up to about 1,500 or so kilohertz. FM is from 80-something megahertz, capital M, capital HZ, up to 100-something megahertz, at least in the United States. I don't know what it is in Europe, probably a little different. Cell phones, you're talking gigahertz, capital G, capital HZ. That's 1 billion cycles per second. And we're going to do a calculation in a few minutes with terahertz, capital T, capital HZ. That would be, what comes after billion? Trillion. 1 trillion cycles per second. We're going to do that in just a few minutes. We're going to do it as a wavelength of light, so let's get down to the business. A few concepts regarding light. Light is a wave in the electromagnetic field. It's different from a water wave or a sound wave. A sound wave is actually energy and momentum propagating through air or through water, if you're talking about sonar. Submarines and whales listening to themselves, swimming through the briny deep, and they listen to sound waves, basically. You can hear all kinds of things in the sea, they say. But light is different. Compasses react to the electromagnetic field. Electrons and protons, of course, are sources of the magnetic field, electromagnetic field. And atoms are held together by the electromagnetic interaction. The proton and the nucleus of hydrogen holding the electron in orbit around the nucleus. Electromagnetic waves form a spectrum. And here's a diagram. There's zillions of diagrams. Just type in electromagnetic spectrum, and you'll see any number of interactive pages and diagrams like this. This is kind of a nice one. Right here, kind of in the middle, is the visible part. The part that our retina is, to which our retina is sensitive, is right in the middle. But over here to the left, gamma rays, X-rays, and ultraviolet. Over to the right, infrared, microwave, and radio. All right. Now, this diagram here below shows the wavelengths, very tight, small wavelengths for X-rays and gamma rays. Very loose, big wavelengths for radio. And visible is kind of right in the middle. So, in order of low energy, radio is lowest frequency, lowest energy. Then infrared and microwave. And some engineers call a certain frequency microwave, other engineers call it infrared. So there's no set, there's a set boundary for visible, but everything else, the boundaries are kind of nebulous. Anyways, higher frequency still is the visible band. It's well defined. We know pretty much the wavelength limits of the visible band. And the famous scientist, Roy G. Biv, famous scientific detective, was notable because his name is the exact order of the colors of the visible band: red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv, the mythological physics professor and scientific detective. A little bit higher energy, ultraviolet. Now here's how I remember the energy. Which is higher energy, visible or ultraviolet? Ultraviolet's what gives you sunburn. You know, you have to have UVA and UVB blockers to avoid getting sunburned. Okay, that tells you that UV, ultraviolet, is more powerful, more energy than visible, right? And it just goes up from there. X-ray, and here again, some engineers might call a certain frequency a hard ultraviolet, and others might call it a soft X-ray. But X-rays are generally higher energy. And then above, I ran out of space, but you can write above X-ray, you can write down. Look at these. This is messed up. Look at that. CAB, CD. Dr. B. Anyway, above X-rays is gamma rays, but I ran out of room because I want to put this in. The speed of light. It's a constant of nature. The speed of light in a vacuum is 3 times 10 to the 8 meters per second. And in theoretical astrophysics, my research area, we use the speed of light all the time. So I know this one, 3 times 10 to the 8 meters per second by heart. 300 million meters per second. Another way to think about it, our star, 93 million miles away, that's 500 light seconds. It takes a photon of light the wand. I got your printout up here. It takes a photon of light 500 seconds to get from the surface of the SUN to Orlando on a sunny day. 500 seconds, roughly. All right, waves. Oscillating systems in general. Why do they oscillate? Let's tackle that. This one's going to be kind of generic. The simplest example of an oscillating system, and one that's easy to use in the lab and do experiments and test things out with, is a simple spring system. You know, like the springs you may have in your car suspension. The springs You know, inside of a ballpoint pen that clicks, you know, you got to click it to extend it outward. The force that the spring produces, either pushing you or pulling you, depends on how much it's squeezed in. You know, how much have you compressed it? How much have you displaced it from its normal rest length? Or the other way, how much have you stretched it from its normal relaxed length? You know, so if the spring is just sitting on the desk, it's going to be at its relaxed length. That's the equilibrium length. If you squeeze it from there, it's going to push back. It's going to want to expand. If you stretch it from there, it's going to want to pull back and shrink back down to equilibrium. And so one way to say that is the more displacement, the more push or pull from the spring. The spring force is proportional to X, and it's a restoring force. It wants to get you back, it wants to get itself back to its equilibrium length, its equilibrium position. So the force is always opposite in direction to the displacement. So if you stretch it to the right, it's going to pull back to the left, back towards equilibrium. Now, I'm going to put up a couple images here. The top image shows a red square object attached to a spring on a tabletop. And let's say that that position where it is there is X subscript 0, and let's say that that's the equilibrium position, all right? And so if I then move the red block out here to the right in the second image, right? It's now to the right of equilibrium. I'm going to get some force back to the left. All right, so my displacement from equilibrium is rightward. The force is leftward. All right. So up here on top, at the equilibrium position, there's no push or pull. It's just sitting there. It's happy as a clam, just kind of resting. But as soon as I pull it out here to the right, I get a leftward pull, right, from the spring, right? And that's what it means to be a restoring force, opposite to the direction of however you move it, left or right. If you move it left, the force is to the right. If you move it right, the force is to the left. All right, so this is an example of position out to the right, force is leftward. By the same token, if you squeeze it down past equilibrium, now to the left of equilibrium, you're going to get some rightward force. And that's because it's going to want to expand. You know, spring has an equilibrium length, and if you compress it, it's going to push itself back out. It's a rigid object. The formula for this, for the force, is fairly simple, minus kx. K is called the spring constant. It's not in the notes, but you can make a note. The letter K is called the spring constant. And the letter K encodes the nature of the material that you're working with, how thick the spring is, how many coils per meter you have, you know, how hard, how rigid is the metal, or how soft is it. If K is big, it means K is measured in newtons per meter. So if you have a spring that gives you 100 newtons per meter, then that's going to be a stiffer spring than a spring that gives you 1 newton per meter. 1 newton per meter, you stretch it all the way out a meter before you even get a single newton of pushback, or pullback, I should say. But if you take the first one and stretch it out a meter, whoa, you got to pull back with 100 newtons, right? You're getting a lot of pullback. So that's the spring constant. The potential energy, fairly simple, 1/2 times the quantity kx squared. That's the potential energy. Here's those last two formulas up here, big letters. F equals minus kx. Spring potential energy, SPE, equals 1/2 kx squared. Anytime we see either of those babies, the force equal to a negative sign times some kind of a constant times a coordinate, that means that the position, that coordinate gives a position, the position of the object at that coordinate is going to oscillate. 1/2 kx squared. Hey, what does that remind you of? No, not gravitational. Kinetic energy. 1/2 mv squared. That is not a coincidence. Go ahead and make a note. 1/2 kx squared and 1/2 mv squared being similar looking, and x being encoded in the v of 1/2 mv squared. All of quantum field theory is based on that correspondence right there. 1/2 kx squared partnering up with 1/2 mv squared. It's kind of cool how it works. But you'd have to become physics majors to learn that. But let's take another look at oscillations. Another factor is, how do you measure the distance of one full cycle? In other words, how big is your oscillation? Caroline, I kept telling her smaller oscillation, smaller amplitude. Right? This is going to be talking about the amplitude of oscillation. So one full cycle means for a given oscillating system, 4 journeys to or from equilibrium. All right? Now the first journey up here in image A, the object is at equilibrium, and the first part of its journey is out to maximum extension. All right? It goes out so far, and then it stops and comes back the other way. All right, here's where it stops. I dropped a dotted line downward to image B. All right, now this box, this square-shaped object, it's out here, and now its motion is back towards equilibrium. So here's another, to or from equilibrium. All right, so this is to equilibrium from max extension, journey number 2. And it's all continuous, but you can think of it as 4 parts of a single journey. But once it gets to equilibrium, all right, here I'm dropping the line down. Here's my dotted line down to equilibrium. Once I get to that, I'm going to overshoot. I'm going to keep going because I'm really motating when I pass through equilibrium. So now, when I get to equilibrium, I'm going to keep going to maximum compression. And let me drop down the dotted line here. Here it is at max compression. This is the inner turning, or the left turning point. There's 2 turning points to the motion. One on the right, one on the left. One of them at max compression, one of them at max expansion. And the 4th segment of its journey is back to equilibrium. And now it starts another cycle. All right? So that adds up to 1 full vibration or cycle of the motion. Now, for reasons of mathematical laziness, scientists and mathematicians use the word amplitude to mean arrows or displacements of this size. In other words, we don't. It turns out that if you use calculus and trig, it turns out to be easier to use half of the full range of motion. So for max compression, you could do everything in terms of max compression to max extension, but it's easier to do it with half of that. And so these 4 arrows, these 4 trips, are equal in length to the amplitude. And so the amplitude of the motion is from equilibrium out to either turning point. Here's another way to look at it. Go ahead and make a sketch of a wave in the ocean, just kind of rolling along out there. It's not breaking, it's not cresting, it's kind of rolling through. Here's sea level, calm day. So the sea on a calm day would be right here where this central line goes through. Here it is, calm sea. And the amplitude is simply this distance from sea level or equilibrium to maximum height above sea level. All right? So the height of the surf above sea level, that's the amplitude. Another way that you could think of it, an equal line segment, is this one. The depth of a trough below sea level. All right? Both of those are considered to be line segments equal to the amplitude. So amplitude is not the full variation, but half of the full variation. All right, so amplitude. Amplitude. Now, let me point out one more cool thing, and that is for the electromagnetic field, we're not talking about ocean waves now, we're not talking about sound waves, we're talking about electromagnetic waves. The energy per second is proportional to the amplitude squared. And that is also related to quantum field theory, a very nice result. So amplitude is something that's important to know. It's not the same thing as frequency. It's not the same thing as period. It's not the same thing as wavelength. It is independent of those. You can have a wave with the same wavelength, but different amplitudes. A big, deep wave, big, tall wave, or just ripples in the pond. Same wavelength, but not so big. Now, speaking of electromagnetic waves, let's work out an example. We're going to do the equation of motion for photons. C equals lambda F. The speed of light is a constant, which we already mentioned. And just a side note, wavelength, that's the spatial dimension of the wave. Period is the temporal dimension, measured in seconds, milliseconds, nanoseconds, any fraction of a second that you want. Frequency is going to be inverse of that, period. So hertz, megahertz, gigahertz, or terahertz. Capital T, capital HZ, that's terahertz. Capital TERA, that's the Greek prefix for trillion. And we're going to do a calculation now in terahertz. So let's, and get your calculator out if you haven't got it, and get your clicker out as well. Have that handy. What we're going to do is calculate the frequency for a red light wave, and this red light wave has the wavelength 656. Now this is the beautiful red H alpha wavelength. Let's figure out what its frequency is. So we'll start with the wave equation, C equals lambda F, and we'll just modify it slightly so that we can get F by itself. And what that means is we'll divide both sides by lambda, we'll get F by itself, and then lambda will be parked underneath the speed of light, C. All right? Now that'll be the formula that we use for the frequency. If we wanted to get the wavelength, lambda, we could use this one. So you might want to jot this one down. C over frequency F equals lambda. They're both pretty easy to use. And lambda is equal to C over F. And frequency F is equal to C over lambda. All right, here we go. F is equal to C over lambda. Okay, here it is. Numerator, C, 3 times 10 to the 8 meters per second. Numerator, 656 nanometers. Oh, Dr. B, you have 10 to the minus 9. Yeah, 10 to the minus 9 is swapped for the little n of nanometers. So when you see little n, you can replace it with 10 to the minus 9. Right? Now that quotient is going to be the frequency. If you have a calculator and you know how to use scientific notation, you can do it right now. I'm going to show you how to handle it if you don't have scientific notation or a calculator. All right? So what I would do is I would take the numeric part, 3 and 656, and then I'd take this 10 to the minus 9 in the denominator and turn it into a 10 to the regular 9 in the numerator. Right? So then you have 10 to the 8 already in the numerator, and now another 10 to the 9 in the numerator. That's a total of 10 to the 17 in the numerator. The meters cancel, numerator and denominator, and you're left with per second out here for your units. Now, per second is the same as a hertz. All right? So I got 10 to the 17. I've got this quotient, 3 over 656, and I've got hertzes over here. All right? Questions about this before we move forward? All right, let's keep going. Now, if you have a calculator, you can calculate this 3 and then the EE button and then the 17. That takes care of 3 times 10 to the 17 up here. And then divide by 656. That takes care of the denominator. And then you hit the equal sign. And what you'll get, depending on the calculator, it might say 4.57 times 10 to the 14, or it might say 4.57 and then a little tiny 14 up and to the right. All right? And your scientific notation button might not be EE, it might say something else. And students, on the exam 3 and the final, you're going to need to use the scientific notation on your calculator. If you have an iPhone, it's pretty easy to use. It's the EE button. And you can mess around with it, but you've got to know how to do it. And you can't use your iPhone on the exams, of course. So you've got to know how to do it. Make sure you get a calculator. But if you don't, if you have to go to pencil and paper, this is how you handle it. Okay, now, notice that this is 10 to the 14 hertz. And so that works out to 457 terahertz. And you may question yourself thinking, Dr. B, how did you go from 10 to the 14 to a terahertz? Well, let's take a look at it. 4.57 times 10 to the 14. That's right here in black type in the middle of the page. And then that's the same as 10 to the 2 times 10 to the 12, right? Because 10 to the 2 times 10 to the 12, that's 10 to the 14. But now, if you keep the 10 to the 12 out here, that's a tera. 10 to the 12, whenever you have one of those, you've got a tera something. In this case, it's going to be terahertz, right? But I've got this 10 to the 2, but 10 to the 2 is the same as 100. And 100 times 4.57 is 457. All right, so there's your 457. Here's the terahertz. And that is how you get that answer. Now, you're going to have some practice in homework 12, which will start in about 20 minutes. It'll be available due on Thursday. You'll have some practice with this stuff, with wavelengths and stuff. Now, I want to get to a few more concepts and basically the heart of today's lesson. But before we do that, I want to draw your mind back to the demonstration of Sean and Caroline And go ahead and answer this question. What is that distance? Half a wavelength, full wavelength, or two wavelengths? Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys did. Correct answer is A. Majority of you got that right. For those of you that didn't, for those of you that did not get that one correct, let me just point out that a wave consists of a bump and then a dip. Right? So this is only the bump. The dip is symmetric but upside down. Right? So that's half of the wave, and the first half is the bump. Okay? So this is a half of a wavelength. Interference. Interference. Write down the word interference. Big, big topic. A lot of cool effects arise from interference of waves. In other words, the interaction of waves. We don't use the word interaction of waves the way we have interaction of skateboarders or interaction of planets. But interference, yeah, we do that. So start with two sources of waves and let the waves move out independently. So two storms at sea, one off the coast of West Africa and one off the coast of Nova Scotia, for instance. And somewhere in the middle of the Atlantic, their waves will interact. Or think about two light sources, two laser beams, or two sources of sound, like our two tuning forks. Now, if you're out in the ocean, at certain points and at certain times, you might have two wave crests that meet, crest to crest. And when that happens, you get a really big wave, super big surf, or what they call out in the middle of the ocean, a rogue wave that can swamp a big freighter. At other points, you might get two troughs that interact, that interfere with each other. And then your trough is extra deep. It's doubly deep. Those two examples are what we call constructive interference. The two waves are interfering constructively. So you get a big peak and a really deep trough, for instance. Now, at another point in the ocean, you might have a location and a time at which a bump, a crest, interacts with a dip, a trough. And when that happens, you have flat water, no wave at all. That is called destructive interference. Now, I'd like to give you some examples, some kind of schematic diagrams of waves moving to the left and right. Here's wave A moving to the right, wave B moving to the left. And down here at the bottom is a snapshot where the two waves at just the right minute, just the right instant when they interact. When they interact or interfere, they interact constructively. The fancy physics term you would say is the two waves are in phase at this location, at this instant of time. But after that moment in time, Wave B keeps going to the left. Wave A keeps going to the right. They don't bounce off each other. They pass through each other. They don't destroy. They don't destroy or magnify either one. The wave B and wave A, they're the same waves. Just heading off in different directions, as they were before they interfered with each other. Now, here's a case of destructive. Let's say that wave A is going to the right, wave B is going to the left, but wave B is a trough. Now, down here at the bottom where they interfere, you would call that flat water or zero amplitude for that moment in time at that location only. It's not permanent, but you would say that the two waves are out of phase at that point, at that moment of time. And then after the flat water moment, ding, they just keep moseying off in the direction that they were going. And that is why you say that energy and momentum are being transported, but not the water molecules necessarily. The water molecules are moving around, but they're not moving with they're kind of participating in the wave, but they're not really moving. You know, a good example is you go to the stadium and they start the wave. The wave moves, you know, around the stadium, but the people don't really move. They just move up and down in their seats, but they're not going from one point to the other in the stadium. They're still in their seats. Okay, so this is a one-dimensional picture of a wave. Now, I have another interference effect that it's important for you to know because it's how the police nab you for speeding. And we've already listened to it. It's the phenomenon called beats. And beats happens when you have one tuning fork slightly out of tune, slightly different frequency, slightly different pitch, slightly different wavelength, and they interact constructively in some places like right here and destructively right here in the middle, and then constructively against over here. Now, this diagram is not very good. I'm going to give you a really good diagram. All right, so here's an example, two waves, slightly different frequencies and lambdas, and I did all this out on a spreadsheet. Your beat frequency is frequency 2 minus frequency 1. Now let me get this. Here's your equilibrium lines. The speed of propagation is 80 meters per second. And I set the frequencies to 106.7 hertz and 119.5 hertz. All right? Now, you can think of these as two waves in the ocean or two audio signals, two speakers. Okay, sound waves from both speakers. Or two tuning forks. Think of it that way. The beat frequency is the difference of those two frequencies. This is what the signal would, this is what you actually hear, the sum of those two signals. The sum of the sound from both tuning forks. This is what you hear in blue, this bottom curve. All right, so this lower curve over here, you have a large amplitude. It's really wiggling. And so you would say here that the sound is really loud. But over here in the middle now, the amplitude for this particular location at this instant of time, the amplitude is really small. You get a lot of destructive interference. So the sound is really faint at that position for this instant of time. Now after that, you're back to high amplitude, loud. And that's why it's had that kind of thrumming, almost like a creepy, scary science fiction movie, you know? Now, let's put in the rest of the data here, all right? Here's the wavelength. If the speed is 80 meters per second and your frequency is 106.7, yeah, your lambda is 0.75 meters. By the same token, for wave number 2, Lambda is 0.67 meters. That is how I designed it. Now the wavelengths are fairly close together. The two frequencies are fairly close, but they're not the same. The beat wavelength is 6.25 meters. Here's the beat wavelength. Make this sketch. From peak to peak. High amplitude peak to the next high amplitude peak. That's the beat wavelength. And what you hear, that kind of drumming low frequency beat, that's the beat frequency. Very small in this case, 12.8 hertz. It's a very low frequency. Now, in your textbook, I want to make one side note. We're in chapter 7 now. This section of the textbook is not a section that I wrote, but it's good. I borrowed it from another author with his permission. You can read all about beats and stuff like that. It'll sound a little bit different than the first part of the book, but it's good. You can use it. Now, next time, we're going to talk about how the cops use beats to nab speeders. You have homework 12 to start in about 5 minutes. You're dismissed. I'll see you on Thursday.